All right, guys, hello. My name is Charlie Vazak, and I work on web performance for Akamai. I'm here to talk about server timing. So back in the olden days of RUM, web page owners who wanted to have fast-loading websites had a problem. The state of the art for performance measurement in those days were eyeballs and stopwatches. And you could answer the question, how long does it take my homepage to load, by using those tools, and you could optimize, and you could try to make the numbers become smaller. But that only gave us one timer from one page load, from one browser, from one part of the world. Because that wasn't enough to give us a realistic picture of how our page loaded, for example, from a low-powered device, using an old version of Chrome, with a cold cache from a 2G network in Timbuktu, for example, we started to introduce a little JavaScript. Now, if you were lucky enough to be in the page before the user clicked to navigate to a new link, you could grab a timestamp, store it in a cookie, as that was the only place that you could store state between page loads, attach a listener to the window.onload event, grab another timestamp, and you could report on the difference as page load time. And that was pretty great too. Aggregating and reporting on the 50th or 90th or 95th percentile was enough to say that you had a fully usable RUM offering. And this number was better because it was real and it had meaning and it was worth optimizing. But if you did want to optimize your site, where do you even start? What is taking all of this time? So in the summer of 2010, there was a platform preview for IE9. And with it, we got the navigation timing API. We were finally able to break up that one big timer into several little timers so we could really isolate what needed to be optimized in order to deliver a faster experience for our users. And then in the fall of 2012, with IE10, we got the resource timing API, with most of these same buckets reported for each individual resource of the page. And I'll add parenthetically that resource timing just landed in the desktop and mobile versions of Safari this year, over 7 years after the first implementation of the navigation timing API. And this is a big deal because depending on where you look, mobile Safari has over a 50% market share for the mobile market. Now, while the navigation and resource timing API give us insight into the work that has to be done from the browser's perspective in order to render a web page, they tell us very little about the work that has to be done by the server or intermediaries to fulfill each request. When it comes to actually producing the bytes and shipping them down to the browser to fulfill the response, all we have are these two big chunks. So here you can see request is defined as the duration from the browser's perspective in between the time they make the request and they get that first byte back on the response. So from request start to response start. Response here is defined as the duration between the browser receiving that first byte and receiving that last byte. So from response start to response end. So I was curious about these two buckets, and I ran a test against the top 25 US sites as reported by Alexa. And my hunch held true. For the majority of these sites, the total time spent formulating the response for all of the resources was 2 to 4 times longer than that it takes to transmit those bytes to the browser. But to get my hands on even more data, I used the data science workbench product that we have. So I queried the beacon data for a few billion resource requests that we had collected from a subset of our major retail customers over a multiple week period. And I don't have a histogram, but the data shows us that for over half of those resources, the request bucket is over 6 times bigger than that of the response bucket. And in a quarter of the cases, the request bucket is over 50 times bigger than that of the response bucket. So what that tells us here is that our diagram isn't drawn to scale. The request bucket should be way wider than the response bucket. So let's zero in on that bucket. We needed a way to further break it up to know what's really going on and took all this time in this black box. The state of the art at this point has been APM, or backend tracing, which kind of lets us do RUM on the server, but correlating that with the RUM data that from our browser's perspective is a little messy. You can correlate server-side logs or server-side beacons with client-side beacons by request ID or refer, but it's really not ideal. Alternatively, if you're already collecting all this stuff in JavaScript from the browser's perspective, for client-side RUM, you can get a little creative. You can capture all that backend tracing data, inject it into the page right before /HTML, as JSON or XML. And then the JavaScript in the page can pick that data up, beacon it back up for ingest, and aggregate it along with all of our other RUM timers. But that only works for base pages, not for sub-resources. How exactly can you pass metadata along with the bytes that make up an image, for example? Well, the solution to open up that black box from a browser standards perspective is server timing. The specification for server timing makes a promise on behalf of the browser. It says that if you write headers on a response in this certain format for all network requests, so that includes base pages, sub-resources, XHRs, and fetches. So if you write the response headers in this certain format, I, the browser, will make the data available to the JavaScript running in the page. Now, this is cool from a web perspective, but when I first got my eyes on the spec, I was really excited about the server timing API for non-web perf reasons. Server timing was promising to be the first server to JavaScript data marshaling API. As a front-end developer, I always found that writing metadata like usernames or config down to the client, I've always found it to be super annoying, fraught with special characters issues, and it was just flat out not super performant. You would have to have your server code serialize your data into something that JavaScript could understand. And remember, JSON.parse has not always been available in browsers. But the ramifications of the server timing API from a web performance perspective are really quite significant. With a few carefully crafted response headers, we were finally able to break open that black box called request. Any machine who touches the response has a chance to annotate it with their own personal timing data, and it will all arrive safely at the browser, where we can finally get a complete picture of the overall work that was completed by anybody, the browser, the server, intermediaries, anybody, to render our page. So here you can see the syntax of the server timing header. As it stands today, a server timing header entry is made up of a required name and a list of named parameters. Parameter values need to be wrapped in double quotes if they're anything more than just a token. And the supported name parameters at this point are duration and description, both of which are optional, which means you can just set down a name. It doesn't have to have a duration and description. All other name parameters that are provided on the response header are just dropped on the floor. They don't get sent to the browser as JavaScript. So on a given response, you can have any number of these header entries, either comma separated or on their own header line. And server timing supports duplicate names per response. But server timing is not everywhere yet. An older version of the API is in Chrome 61 behind a feature flag. In Chrome Canary, there's a version of the API that uses a slightly different header format than the spec describes. But by Chrome 63, which is scheduled to be released by the end of the year, version 1 of the API should be enabled by default. I hacked together this fake can I use visualization, and it's not pretty. But it's going to get better. And in my opinion, I think we should all take this time now to instrument our backend systems with server timing now, so that when it is finally supported by Chrome and then all the other major browsers, we'll be ready to take advantage of all of this data that we've been generating. Implementation for WebKit has already begun, and so with luck, that should land by the end of this year. And I hope that Firefox and IE will follow fairly quickly. All right, so what should we be measuring? What processing in our app's backend systems do we need to time? Well, the truth is that no one knows your app as well as you do. The developer of the app is best equipped to identify bottlenecks in processing web requests in the wild. When in doubt, instrument it. In the end, you cannot optimize anything until it can be measured. Okay, show of hands here. Is there anybody yet using the server timing API from the browser perspective? Is anybody using user timing at all? Nick is using server timing or user timing. Okay, so just like user timing API, you don't really get anything for free. You actually have to write these response headers to get the server timing entries marshaled down to JavaScript land. But unlike user timing, data from server timing needs to be generated and written from a different platform than from where it's actually read. As responses are handled by hundreds of different languages, different types of programs, and any number of operating systems, there is no native support to inject these headers. But thankfully, there are a lot of tools that make this really easy. All right, so I personally really love Express for Node because it's super lightweight, and it's very easy to use and configure and extend. It's definitely my go-to web server when I'm trying to prototype something or any kind of side project that I'm working on. So a few months ago, I had the idea to write a middleware package that would run in Express that would make writing server timing entries super easy. But just before hitting enter on my npm init command, I decided to check npm just on the off chance that someone had already beaten me to it. I thought this was pretty unlikely because the spec was still in flight and no browser even supported the API, but I checked just in case, and I searched, and there wasn't one. There were 5, but none of them did exactly what I wanted. They basically all just provided a .start, .stop API. And all of them would then use the popular onHeaders package, which would write out the timers that they had collected for that request just before the response hit the wire, which is nice and definitely table stakes, but I wanted more. Because it's JavaScript and fairly easy to step through, I had the hunch that you'd be able to get at the internals of Express in such a way that you could get at least some time measurement for free. So, against my better judgment, I added a 6th Express middleware package on npm with this super terrible long name. It is sadly not super popular, but if you run Express, you should really give it a try. So, of course, here you can see that it has the obligatory .start and .stop interface methods to the response object, but it also has 2 things that no other module does. Here you can see I make an API call that I know to be potentially time-consuming. So I take that potentially slow block of code and I wrap it in a function. I pass that method to the library. The library adds a method on the response object called server timing sync. You pass that function to server timing sync. The middleware will execute that code, timing how long it takes for that block to execute, and then it'll write a response header with a name and description of your choosing to that response. So that's cool. And secondly, by hacking at some of the Express internals, which is dangerous, the library will actually create a server timing entry for every piece of middleware that executes that takes more than 1 millisecond. And that's the free. Just by requiring my node module before the .listen call, you get automagic middleware instrumentation out of the box, helping to identify which middleware might be causing you performance problems. At the very least, it'll help you to identify which middleware package that you should further instrument with server timing. Okay, so for Express, we more than have you covered for server timing middleware libraries, which is great. But what if you're a Ruby on Rails shop? Well, if you're running Rails 3 or higher, there's a gem with an MIT license that will help you get started with server timing. The library uses active support instrumentation to write out a server timing entry for the total time it took to respond to the request, as well as entries where it breaks down the other runtime benchmarks. Or if you're running an ASP.NET app, there's a package on GitHub with an MIT license that should help you get started. The library runs a request scope service, which listens for timers from your code, and then it runs middleware to write the timers to the response header the last possible moment, right before it hits the wire, using HTTP response.onStarting. So one last note for writing these headers, and this is true regardless of stack or framework. You need to be sure to be a good citizen when it comes to response headers. Because any number of intermediaries might have run before you, you need to be sure to append your server timing metrics to the response, leaving those entries that came before you intact. When I was doing my NPM sleuthing, I noticed that most of the NPM packages made the mistake of using response.set headers, which totally blows away any entries that might already be there. So if you are writing server timing headers manually, it's best to write out the headers on a brand new line or concatenate them with strings. But you really want to be sure to leave anybody else who's there before you intact. Right. Now, of course, whenever there's talk of a new browser API, you can't get very far with talking about the technology before you have to talk about privacy and security. Now, in the case of server timing, in my opinion, it's less of an issue because unlike resource timing or some of the others, there are no server timing entries written to the browser unless you or your intermediaries write them to the response header. And the origin ultimately gets to decide what goes out on the wire. So from a browser's perspective, resources of a page fall into one of two buckets. They are either same origin or cross origin. Technically speaking, for a resource to be same origin, the protocol, host, and port need to match exactly that of the document. But from a development perspective, resources of a page fall into one of three buckets. They're either same origin, cross origin where you do control the alternate domain, or cross origin where you do not control the alternate domain. For same origin resources, you get the complete picture of performance for resource timing and server timing APIs without having to do anything, which is great. But for cross-origin resources where you do control the alternate domain, most likely for domain sharding, you need to write down a permissive timing allow origin response header. Otherwise, the browser will strip out all of the bits about resource timing and server timing that could be considered an attack vector. For resource timing, basically anything that provides any more information than can be obtained by hooking into the onload or on-air handler is stripped out. And for server timing, it's just the mere presence of a response header with a particular name is enough to convey Boolean information. If the tau isn't sent in a permissive way, the entire entry all of the entries for that resource are dropped on the ground, dropped on the floor as if they never happened. So if you host your web page on www.example.com, for example, but use images or web fonts or scripts from static.example.com, be sure to write down this explicitly permissive timing allow origin response header on all of your static resources and XHRs. For cross-origin resources where you do not control the alternate domain, you need to reach out to those providers to ask them to write an even more permissive response header, if they aren't already. Examples of this would be calls to analytics.twitter.com or googleanalytics.com or JavaScript or web font CDN. Only when these third-party domains decide to play nicely with this permissive response header will site owners truly be able to get a complete performance picture of the resources that make up their sites. Okay, at this point, you've instrumented your app with server timing. You're measuring all of your backend service code that could have performance implications and shipping that data down using response headers to the browser to perform all the analytics that you need. But presuming that you're sitting behind a CDN, all of that instrumentation that you've done is done at the origin. And a super high number of all of those calls are going to be offloaded by edge. So unless we do something at the CDN level, we're back to this response as a black box situation from earlier. So while stopping short of implying CDN level best practices for server timing usage, there are three entries that we're looking into emitting across the board for all of the requests that run through our networks. These are timers and metrics that, in my opinion, all CDNs or companies with CDN-like services can and should report on themselves. Okay, firstly, edge time is a concept that I would like to see CDNs expose for every request that passes through their networks. Edge time is measured at the CDN box that sits closest to the browser and is defined as the duration between the moment that the first byte of the request hit that box and the moment just before the first byte of the response is to be written out. The edge could have the resource in cache, or it might have to go to a parent, or it might have to go all the way back to the origin. Regardless, all of that time would be included as part of edge time. Note that I'm not suggesting that CDNs write out where the resource was served from, or from which tier, or sibling, or parent, which could reveal some secret sauce about the CDN. What I'm suggesting is that the time indicating how long it was spent at that closest box to the browser provide enough insight that you can analyze how much work the CDN is doing on your behalf. Okay, secondly, indicating, and here's an example of a header with no timing at all, even though it's called server timing. indicating if a resource was either served by origin or if it was served by cache anywhere within the CDN is incredibly powerful information from a RUM perspective. We can already kind of backdoor the resource timing data to determine whether or not a resource was cached in the browser, but supplying this bit about the origin using server timing would allow analytics providers to bucket all of the requests by whom they were ultimately served. It allows you to monitor the cacheability and cachedness of the resources that make up your pages using RUM. You can set up alerts on cache regressions or watch trends over time and seasonality and get an overall picture as to how much work your origin is actually being asked to do. Okay, so everybody knows that there are many services that do on-the-fly resource optimization and compression and offload. Compression and optimization the same. Using resource timing data, we can know the final result of those techniques. For resources that do pass the same origin policy that the browsers enforce, we know the number of bytes that actually went down over the wire using transfer size. And if nothing actually went over the wire, because the resource was already in the browser cache, we know the encoded body size of the resource as it sits in the browser. But wouldn't it be great if our analytics code could know the original size of the asset? Wouldn't it be great to know how much data that these CDN optimization techniques were actually saving our actual users? We will be able to correlate data compression to any of our other business metrics and really see how much value we're getting out of these CDN or CDN-like service features. Well, that's exactly what I'm proposing here. Services that provide on-the-fly resource optimization and compression could emit the original disk size as a server timing entry called bytes. So for RUM and Mpulse, which is Akamai's RUM offering, we're playing around with exposing these 3 server timing header entries. But the truth is, if you want to get started, if you want to see for yourself the insight that this data can provide you, you can do this today using advanced metadata. All right, and that is exactly what I'm doing on a demo site. All right, so this is an Edge Store demo site that we stood up. You might have seen in some other demos. So for all of the resources and the base page and XHRs of the page, I'm writing down those 3 server timing metrics. Let's take a look at what it looks like in the browser. How do you right-click on your machine? There we go. Slow press. Okay, so what was it? 2 fingers? Okay, so DevTools offers the ability to add any custom header in a first-class way. So I'll add server timing, and you can see that I'm writing these server timing entries on the base page and all of the images. So if I go over here to doc, you can see the base page. It was served. It was served by edge because origin is false, and the edge time is 127. If I look at some of these images, you can see that they were served by edge. You can see their original disk size, and you can see the total edge time. All right, I think I installed TemperMonkey in the other machine. That's okay. All right, so let's take a look at this some more. So you can also mouse over these resources, and you can see the server timing entries down here at the bottom of the waterfall. So now Chrome DevTools makes an assumption that all server timing entries are meant for time. So they assume that all entries have a duration, and that duration is a time value, and that time value is in milliseconds. So you can see here for false and 4841, their assumption kind of falls over a little bit because I'm using the server timing API to communicate metadata to my client. Okay, so that's what they look like in the network tab. And let's take a look at this in JavaScript. So here's all of so the first entry is, hopefully you're seeing this, the navigation timing entry. And Yo does not have experimental web features turned on, but I can tell you that there was an older version of the API where server timing entries were emitted as their own standalone thing. So they were emitted just alongside of the navigation timing entries or the resource timing entries. But I wrote the code to try to correlate those server timing entries with their resource, and it was a mess. So we went back to the spec and we decided to have the server timing entries hang off of their navigation and resource timing entries, which is where they belong. So as you can see, there is a lot of data being produced for these entries, and we'll talk about that later. All right, so DevTools helps a lot. You didn't get to see it all, but we can see all the headers that we've written out of the base page for all the sub-resources and XHRs and fetches. But now it's time to read all these timers and metrics for all of our users, wherever they are in the world, and beacon that data back up to our collectors for ingest and aggregation. And this will allow us to analyze our RUM data and correlate it with business metrics like session length and session duration and conversions. But we also need all of that resource timing and server timing data that you saw that I showed you in DevTools. If we're trying to diagnose one particularly poor performing user experience, for example, averages and percentiles aren't going to help us. What we really need is the ability to recreate the waterfall that you saw in DevTools back in Impulse. And that's a lot of data. But thankfully, there are 3 open source libraries that make this really easy. Boomerang is an open source RUM library written in JavaScript, started by Philip Tellis back when he was at Yahoo in 2010. Impulse, Akamai's RUM product, uses Boomerang to collect timing characteristics about the page and beacon that data out of the browser for collection. Now, Boomerang works in browsers back to IE5.5, but obviously it provides the most insight when the browser supports the resource and navigation timing APIs. As you saw in my demo, when you pop open the DevTools of a page, the amount of data that the resource timing API produces is staggering. To be able to reproduce a waterfall to millisecond precision for Akamai.com, for example, that would take 120K of data. Now, there's been a lot of talk in the W3C community about providing access to the gzip capabilities that browsers already have natively. So what I'm talking about is gzip from JavaScript, and that will be awesome. But until we have that, we're lucky to have this, resource timing compression JS. So this is an open source library started by Nick Jansma when he was at SOSTA in 2014. Boomerang uses this library to collect and compress all of the resource timing entries on the page. It walks the DOM, stepping into every iframe that it has access to, harvesting the resource timing entries. Once collected, it applies custom compression techniques to the data to convert the array into a JSON structured radix tree. The amount of data that must be transmitted out of the browser to be able to draw that waterfall that we're talking about goes from about 120K to 15K. It's an 88% data savings. To learn more about this compression algorithm, check out Nick's blog at nickj.net. So as of a few months ago, resource timing compression JS now also handles the server timing entry array. So the server timing bits around the compression algorithm are built around the assumption that you're writing out these server timing headers, the same server timing headers for most, if not all, of your resources. So it correlates, it creates tuples of names and descriptions and beacons that alongside the resource timing data. And then it leaving just the duration that a server timing entry took along in the resource timing tree. So Lastly, to really squeeze all of the savings on the wire that we can, we use JSURL, an open source library that generates URL-safe serialized JSON using less bytes than JSON.stringify. So using this library and the resource timing compression library, we get down to about 10K. All right, so for my edge store site, Mpulse is the Akamai Run product that is going to collect and present the data associated with all my beacons. The power and the insight that Mpulse provides are built around timers, metrics, and dimensions, if you haven't seen the product. So out of the box, Mpulse gives you timers, like page load time and DOM ready, and a breakdown of front end versus back end. It gives you access to metrics like session length and DOM node count and resource count and domain count. And then you can slice and dice your data by dimensions like geo or device type or browser or OS. So Mpulse makes it very easy to complement this out-of-the-box features with custom timers, custom dimensions, and custom metrics. And that's exactly what I've done with my Edge store. I've written a Boomerang plugin that collects these CDN-injected server timing metrics and beacons them back in a first-class way. And I'm using Mpulse to collect, aggregate, and visualize these numbers. All right, so I'm going to pop over to Mpulse. And I have a dashboard called CDN server timing that is going to show some of these numbers for my Edge store. Okay, so there's a lot going on in the dashboard, but it shows edge time for the base page. It shows an aggregate edge time. So let's start at the top row until it goes away, and it's going. But we have edge time. We identify the total number of resources, those that are served by browser, edge, and the origin. It allows us to do offload metrics in kilobytes and percentages. And then lastly, the bottom row, which is really ugly, it shows the total amount of savings that Image Manager is doing for us. All right. So let's talk about the future of server timing. I'm a member of the W3C Web Performance Working Group, the group that has been working to spec out many of these RUM APIs. And the feedback that the group has received from this point about server timing has been extremely positive, but we do get a lot of questions about start time. So if you think about the navigation timing, resource timing, user timing APIs, they all have a concept of a start time, which is to say something that roots the duration. And in most cases, it's the navigation start. So what people really want to be able to do is draw full server-side waterfalls. And the concept of a start time is a little trickier for server timing because servers and intermediaries don't know when the request was started, and they don't know when the page was navigated to. On top of that, nowadays, there is really no one server. So the start time from one server is not going to make any sense to the start time of another server. But, and this is obvious when you break open the DevTools in Chrome. Sure, they show horizontal bars representing the server timing entries, but they have no start time, so they're all just pushed to the right. So the visualization helps you understand that which server timing entry was longer than the other, but they're not rooted in anything. So what I can tell you from a W3C working group perspective is that without making any promises, we've heard these requests and we're working on it. So version 1, which is the version that should land in Chrome by the end of the year, uses a header format that's very extensible. And this was very much on purpose. We went with the named parameter format so that adding later parameters is going to be very natural. Future parameters could be things like server name or server ID or start time and anything else that might be required to recreate a per server side waterfall in the client. Okay, before I wrap up, I would like to plug a demo that Nick Jansma and I have been preparing. So come see us out in the dev zone. This is the perf bar that I was trying to demo that failed me. On the far left, you see the timing buckets that you should recognize from the resource timing request response flow. And you can see that, I can't see the number, but our request bucket was 168 milliseconds wide, and the edge time for that base page was 103 milliseconds. So you're also able to backdoor the network time up and down. And then on this far right, we see that there were 48 resources, 43 were served by edge, with a cumulative edge time for all 43 of those resources being 51 milliseconds. So the other thing Nick is going to be talking about are our continuity metrics. So things like time to interactive, which we're trying to define in RUM for the first time, rage clicks, and how we're using long tasks to help define when time to interactive happens. So this is out in the dev zone. We'll be around all week. Please come see us. I'll have it working then. So if you want to learn any more about these things, come find me. I'm going to be in the dev zone. I would love to talk about how server timing can help you to monitor the performance of your site. And that's it. Thank you. Thanks for bearing with us.